Welcome to the Foundry by Forge College. Today, we're grabbing our hard hats and digging back into the Cloudbreak blueprint. Now, we're building directly on our previous explainer about its core architectural components. We all know Cloudbreak is Solana's state storage engine, right? But how does it actually organize all that data under the hood? Like, how does it keep everything moving at absolute lightning speed without just bogging down completely? Well, today, we're going to map out those exact pathways. Here is the facility floor plan for today's explainer. We'll kick things off with an introduction to the layout, then move into logical segmentation, trace the lookup path, dive into real-world access patterns, establish our mental models for indexing, and finally we'll wrap up with key takeaways. All right, Section 1, Introduction to Cloudbreak Layout, focusing on the interface, index, and persistence layers. So think of Cloudbreak a bit like a highly efficient, well-run restaurant. You've got your interface acting as the front of house, taking the orders. Then there's the index, which is like the ticket system, routing those orders to the right place. And finally, persistence. That's the deep freeze in the back. Because Cloudbreak actually separates these functions out, every single layer can be optimized independently. The interface gets tuned for pure speed, the index for compactness, and the persistence layer for rock-solid durability. But before we get too deep into the layout, you really need to understand namespaces. Basically, think of a namespace as a zip code for your data. It's a logical partition that maps an account key hash or program ownership to one or more physical storage shards. It's this crucial mapping layer that keeps data routing totally predictable. So when we have to balance the load across servers, the namespace map tells the index layer exactly where it needs to look. It's honestly the linchpin for efficient lookup and safe, low-latency reconfiguration. Moving right along to Section 2, Logical Segmentation of State, or dividing up the floor plan. Cloudbreak doesn't just throw all its data into one messy, chaotic pile like a teenager's bedroom. It neatly divides the state into 3 primary, highly functional segments. And this segmentation is huge because it reduces contention and improves cache locality, meaning the runtime can request exactly the segment it needs without tripping over completely unrelated data. So first up, account state gets low-latency hash maps, simply because it requires frequent single-key lookups. Then you have program binaries, which get memory-friendly caching, since they're super read-heavy when executing code. And auxiliary blobs? Well, those are large, bulky items, so they get a pointer index and are just shipped off to cold storage. I mean, you wouldn't store your winter quotes in the kitchen pantry, right? In the exact same way, Cloudbreak doesn't store cold blobs in hot memory. Which brings us to Section 3, Tracing the Lookup Path. Think of this as our treasure map. Every single lookup in the system follows this exact step-by-step navigation path. First, it computes the key hash. Second, it consults that namespace map we talked about to find out which logical shard actually owns that key. Third, it checks the shard local index to see if the data is already hot, sitting in the in-memory cache. And finally, step 4, if it's not in the cache, it grabs the physical storage pointer to pull it directly from the disk. Hash, map, index, pointer. It's a beautifully choreographed dance, and it literally happens millions of times a second. All right, Section 4, Real-World Access Patterns. It is time for some stress testing. To figure out how this beautiful architecture actually holds up under wildly different workload shapes, we're going to track 3 distinct scenarios that network engineers see every single day. Scenario 1, a simple balance check, which is a single account read. Scenario 2, a massive node recovery, otherwise known as a multi-account snapshot read. And Scenario 3, a hyperactive smart contract, representing write-heavy hotspot updates. Let's see exactly how Cloudbreak handles the pressure. Okay, so in Scenario 1, let's say you just want to check your wallet balance. For a single account read, absolute speed is the single highest priority. You want that answer yesterday. So the system just darts straight through the namespace map, heading directly to the shard local cache for a near-instant return. It completely skips bulk storage to ensure low latency and minimal input-output operations. It's pretty much exactly like using the express lane at the grocery store. Now, Scenario 2 is a completely different beast. When you're recovering a node that just booted up, checking accounts one by one is painfully, terribly slow. So the system opts for bulk reads instead. It utilizes packed checkpoint bundles for high-throughput sequential I/O. So rather than grabbing single items one at a time, it's loading entire pallets of data all at once. The system happily trades away those quick single lookups for massive throughput just to get that node back online fast. And then we have Scenario 3. Say there's one incredibly popular gaming or DeFi program that just won't stop writing, creating a massive hotspot on the network. Cloudbreak doesn't panic. Instead, it batches the index updates and uses append-only logs. So instead of updating the main database immediately for every single microtransaction, it just jots them down in a fast append-only ledger to avoid a complete traffic jam. Then it updates the shard local index in bulk a little later. Looking at these three wildly different behaviors, the express lanes, the pallet loaders, and the batch processing, you really have to ask yourself a critical engineering question. How do you actually decide which indexing strategy makes sense for your specific build? Because the reality is you can't optimize for everything all at once. So let's open up the Engineer's Handbook in Section 5, Mental Models for Indexing. Layer 1 of this mental model is classifying your access class. You have to ask, are most of your operations latency-sensitive single keys, or are they throughput-hungry bulk operations? Single key operations absolutely require hash maps and strong caching, while bulk operations demand sequential I/O and packed snapshots. You basically just have to pick your lane. Layer 2 then maps that specific workload to index properties. You have to understand that achieving a really low lookup cost means spending way more of your system's budget on memory and caches. Conversely, if you want fast, cheap writes, you need to rely heavily on append-only logs. And if your system needs sequential reads, you have to organize your storage in a range-ordered way. Listen, there are absolutely no free lunches in state storage. You're always trading memory, disk bandwidth, and background processing against latency and durability. And finally, Section 6, Key Takeaways and Next Steps. Let's roll up this schematic. So the most crucial thing to remember today is this 3-step takeaway. Number 1, always match your index to your workload shape. Number 2, dial your snapshot frequency to balance your recovery speed versus your write cost. It is a massive throughput lever for your system. And number 3, shift those namespace boundaries or use replicas whenever specific shards overheat from too much traffic. Because, as the saying goes, the mapping between access patterns and Cloudbreak's logical layout is where performance and scalability decisions live. If a sudden latency spike is ruining your weekend, you don't just guess what's wrong. You map the symptom directly to the lookup path. Are your index CPUs totally maxed out? Are you hitting a cache miss wall and having to drag data off a slow, cold disk? The mapping between access patterns and Cloudbreak's logical layout is exactly where your real performance decisions live. So definitely keep this blueprint handy, because our next explainer is going to connect these exact access patterns to the physical costs of coordinating shards across a globally distributed network. We're going to take everything we just learned today about local shards and scale it up to the entire system. It's going to be great. But before you go, I want you to think about this. If you had to optimize Cloudbreak for a massive, sudden airdrop event, like where millions of tiny writes hit the network at exactly the same second, which indexing lever would you pull first? Think about how you'd handle that crazy, sudden traffic using the mental models we just covered. To explore the answer to that, and to dive way deeper into other advanced Web3 topics, be sure to visit forge.college to continue your learning journey. Thanks so much for joining me on this explainer, and I will see you in the next one.